All right, get ready for an algorithm showdown. Today, we've got three heavyweights of computer science stepping into the ring. They're all trying to solve one of the most classic problems out there, finding the shortest path. It's Dijkstra, Bellman-Ford, and Floyd-Warshall, head-to-head.
I mean, think about it. Every time you use your GPS, or every time a piece of data zips across the internet, there's a core question being asked. What's the best way to get from A to B? Is it the fastest? The cheapest? The most efficient? Well, these three algorithms are the brains behind the answers.
So, here's how we're going to break it down today. First, we'll nail down exactly what this shortest path problem is. Then, we'll meet our three contenders and pop the hood to see how they tick. We're going to put them through a really tough stress test, check their performance, and then, for the grand finale, we'll help you figure out how to choose the right champion for your job.
Okay, first things first. What exactly is the problem that we are trying to solve here?
Let's make this super simple. Just picture a map. You've got cities. In graph terms, we call those vertices, and you have roads connecting them. Those are the edges. Now, each road has a weight, which could be the travel time or the distance or even a cost. The shortest path problem is just finding the route from your starting city to your destination that adds up to the smallest total weight. That's it. It's really that intuitive.
All right, it's time to bring our contenders out. Each one has its own personality, its own strategy, and believe me, its own strengths and weaknesses.
So let's check out the tail of the tape. First up, we have Dijkstra, who I like to call the optimistic sprinter. Super fast, but has a pretty major blind spot we'll talk about. Then you've got Bellman-Ford, the cautious detective. It's slower, for sure, but it methodically checks every single clue. And finally, there's Floyd-Warshall, the grandmaster strategist. This one's playing a different game. It doesn't just find one path. It calculates the best route between every single pair of cities on the map. The whole shebang.
And you know what's crazy? These ideas aren't new at all. The very foundation of modern routing was basically invented in just a few short years, back in the late 50s and early 60s. And get this for a fun fact, the legendary Dijkstra apparently came up with his algorithm in about 20 minutes while just sitting at a cafe. Incredible. So, we've met our contenders, but how do they actually do what they do? Let's get into their core strategies. Dijkstra's approach is just elegant. It's what we call a greedy algorithm. Imagine it starts at your home base and builds this expanding cloud of places it knows how to get to. At every single step, it just asks a simple question. From everywhere I've explored, what's the absolute closest new city I can get to? It grabs that city, adds it to the cloud, and then, here's the key, it relaxes the edges to its neighbors. That's just a fancy term for checking, hey, does this new spot I just found give me a shortcut to any of its neighbors? This greedy, always pick the closest strategy is what makes it so darn fast.
Now, Bellman-Ford, totally different beast. It's not greedy, it's methodical. It repeatedly sweeps through every single road on the entire map over and over again. It does this v-1 times, where v is the number of cities. And each time it sweeps through, it relaxes every edge, potentially finding slightly better paths. It's like a detective who keeps re-interviewing all the witnesses until the stories stop changing and the truth finally emerges.
And then we have our grandmaster, Floyd-Warshall. This one's on another level. It starts by making a big chart of all the direct travel times between cities. Then, it goes through every single city on the map, let's call one K, and it asks a really simple question for every other pair of cities, say I and J. Is it shorter to go from I to J if we make a stop at K? By doing this for every possible city as a potential layover, it systematically fills in the blanks and ends up with a complete map of every best path.
Okay, so at this point you might be thinking, Dijkstra sounds amazing. It's fast, it's pretty simple. Why would I ever need the other two? Well, this is where things get really interesting. Let's introduce a twist, a critical test where our optimistic sprinter completely falls apart.
See, on a normal map, where travel times are always positive numbers, it always takes some time to get somewhere, Dijkstra is flawless. It finds a path, locks it in, and knows it's the best one. Because any other path would have to go somewhere further away first. It just works.
But what if the weights on our roads aren't times? They're costs. And what if one of those roads has a negative cost? Like a toll road that actually pays you a rebate to use it. This is what we call a negative edge weight. And for Dijkstra's optimistic logic, this breaks everything.
Here's the core problem. Dijkstra's logic depends on this one big assumption. Once it finalizes a path to a city, it's the shortest path, period. But a negative edge is like a secret portal. You could find a path to a faraway city, take that road with a big rebate, and suddenly you found a cheaper way back to a city that Dijkstra thought it had already solved. Its greedy choice was wrong. The whole assumption falls apart. And that is when you need to call in the cautious detective, Bellman Ford.
And believe it or not, it can get even weirder. What if you find a loop of roads where the rebates are so good that you actually make a profit every time you drive around it? That's a negative weight cycle. You could just keep driving in that circle forever, making your path cost infinitely small. The whole idea of a shortest path just ceases to exist. And this is Bellman Ford's hidden superpower. After it does all its sweeps, it does one final check. If it can still find a better path, it knows a negative cycle exists and it raises the alarm.
So Bellman Ford is way safer when things get weird, but that safety comes at a price. And that price is performance. So now that we know their strategies, let's put them on the clock.
Okay, don't let the big O stuff scare you. It's just a way of measuring how much slower an algorithm gets as your map gets bigger. V is the number of cities, E is the number of roads. You can see right away, Dijkstra's our speed demon. Bellman Ford is chunkier. Its time is based on cities times roads. But then look at Floyd Warshall. V cubed? Wow, that's just in a completely different league of slow.
And this chart really drives home what V cubed means in practice. I mean, look at that. For a small map, yeah, they're all kind of in the same ballpark. But as soon as your graph starts to grow, that V-cubed runtime doesn't just climb, it hits a vertical cliff. It explodes. This is why Floyd Warshall is really only practical for smaller graphs.
All right, we've seen how they work, we've found their fatal flaws, and we've timed them. It's time for the final round. How do you pick your champion?
The choice for Dijkstra is pretty straightforward. You use it when you're starting from one spot, speed is absolutely critical, and, this is the big one, you are 100% sure all your edge weights are non-negative. No rebates, no weird fees. Think Google Maps, basic network routing, this is your go-to.
So when do you call in the detective? You use Bellman Ford when the map gets murky. If there is any chance of negative weights, or if your entire goal is to find those infinite money negative cycles, like looking for arbitrage opportunities in currency markets, then you have to use Bellman Ford. You're trading speed for correctness and safety.
And finally, our Grandmaster, Floyd Warshall. You bring this one in for a very specific mission, when you need to know the shortest path between every single pair of cities. It's fantastic if you have a small, dense map and you want to pre-calculate everything up front so you can get answers instantly later. But here's a little pro tip. For a big map that's sparsely connected, it's often way faster to just run our sprinter, Dijkstra, once from every single city.
So in the end, there's no single champion, just the right tool for the job. You now have the keys to pick the right contender for pretty much any static map. But that leaves us with a final, lingering thought, doesn't it? What happens when the map itself is constantly changing? When traffic jams pop up or roads suddenly close? Finding the best path in a network that changes every second, well, that's a whole new ballgame.